Hello and good morning, everybody. Welcome to this session on spatial data. Please hurry, come in, otherwise all the seats are occupied and you have to stand in the aisle. My name is Holger Teisel. I'm going to chair this session. We have 6 rather diverse papers about the topic spatial data. And the first paper is called Real-Time Visualization of Large-Scaled Geological Models with Nonlinear Feature-Preserving Level of Details. And the authors are from KAUST University, Ronel Sikas, Mohamed Ibrahim, Amani Ageli, Florian Manus, Peter Rautek, and Markus Hartwiger. Ronel is going to give the presentation. Let's go.
All right. Good morning, everyone. So welcome to my talk about visualizing geological models. My name is Ronel Sikat from KAUST, and this is joint work with my collaborators from KAUST and Aramco. So geological models are very important in many fields, such as the geosciences and the oil and gas industry. So they're usually used for flow visualization, as we can see here. And in our work, we focus on hexahedral meshes with attributes, in particular the corner point grid format, where the corners lie on a straight line called pillars, and we have mesh discontinuities called faults, and each cell has one or more attributes, such as temperature and porosity. So with the increase in the sizes and complexity of these data sets comes the need for multi-resolution visualization and analysis. However, standard level of detail approaches can still have problems. So for instance, naive averaging and subsampling can introduce unwanted unwanted values on the attribute edges and can have disappearing faults. So this is similar for subsampling, so you can also have disappearing faults if you're not careful. So there's a more recent approach called hexashrink that uses wavelets. So they're able to better preserve faults, but you can still have issues on the attributes. So the main problem with these approaches is that they use linear translation invariant filter for computing the coarse levels. So if you imagine, for example, you have an edge feature on this 2x2 pixel neighborhood, it gets replaced by a single value that's the weighted average of these pixels, and you lose the edge feature. Yeah, and this is kind of similar to what happens with wavelet techniques where the approximation coefficients are used in coarse levels. So to solve this problem, we completely decouple the detail reduction stage from the storage reduction. So during the detail reduction, we keep the number of samples the same across resolution levels, but we reduce the detail content. And we do that using a nonlinear filter, which I'll talk about later. But as you can imagine, you have more control over the amount of features that you can keep across levels. Now, after the detail reduction, we perform the storage reduction in a completely separate stage. And since we reduce the detail across levels, naturally, the amount of information you have to store goes down. And in our case, we use a wavelet compression. So this is just one of the key ingredients in our approach. And this is our whole framework. So first, we map the geological model to an image representation. Then we apply the nonlinear filter. And then we apply wavelet compression to encode the images into our data structure. And then we can use the data structure for GPU rendering. All right, so now I'll go into the steps in a little bit more detail. So the first step, we map the geological model data into a multi-channel image stack, which we call geometry images. So each pixel here corresponds to the corners of the data. So it contains the corner vertices and attribute information. So this is kind of how the image channels look like. And with these channels, we can now apply our joint bilateral filter. And the job of the joint bilateral filter is to progressively reduce detail. And you have a lot of control over how much you reduce the detail. And this is kind of an example result of how this smoothing works. So you can see that the important features are still preserved. And you apply this progressively to the data to get kind of a multi-scale representation. And this is kind of a color example to give you an intuition of that multi-scale hierarchy. So once we have that, we now encode the images into the GPU. So we first split the images into what we call tilets, just a smaller region. And then each tilet, we compute the discrete wavelet transform, and finally encode the wavelet coefficients using the progress encoding algorithm. So we do this for all the levels and store this compressed wavelet coefficients in the GPU. So now we load that data structure into the GPU, which we can directly use for our GPU rendering pipeline. So this is how it looks like. So first, we perform visibility culling. And for each visible tile, we look at the wavelet coefficients. If they're sparse enough, we just load a few tilets and basically generate a few triangles for this region. And for more denser wavelet coefficients, this corresponds to like higher feature regions, so we generate more geometry for that. So this makes sure that we can adapt the geometry according to the feature contents in the mesh and the attributes. So it's important that we consider both the mesh and the attribute content, as you'll see in the results later. So yeah, now I'll talk a little bit about the results. I'll just show a few of the results here. You can take a look at the paper for more results. So first for the colors here are a bit weird. But anyway, so here you have the original data on the top left and the faults visualized on the bottom. So if you use subsampling, the faults start to disappear pretty quickly. And if you use the wavelet approach, the faults are maintained, but the attributes and the mesh get aligned really quickly because they are processed separately. So if you look at our approach over here, the first thing you'll notice is that the geometry is adaptive. So each color box here that you see roughly corresponds to 100 triangles. So the mesh adapts, the geometry adapts to the feature content. So for example, here, if you look in the lower left region, there's a fewer triangles there when we switch to a more, let's say, smooth or flat attribute. And yes, overall, because we are able to adapt the geometry, we can basically preserve the important features better. Now, as you can imagine, because our approach tends to render more triangles than the standard approaches, our approach can be a bit slower, especially for smaller data sets. But for larger data sets, we are able to handle the data set still, but the standard approaches will not be able to. And this is mainly because we can squeeze in up to, let's say, 30 times more data into the GPU compared to other approaches. And for storage purposes, we can also compress the data up to 12x, depending on the feature content of the data or frequency content. So yeah, just to summarize, we introduced a framework that jointly preserves mesh and attribute features in real-time visualization of geological models. And this is made possible by mapping the mesh and attribute data to geometry images, applying nonlinear smoothing filters, using wavelet-based encoding, and adaptive rendering using task and mesh shaders. Thank you.
Thank you very much, Ronel. We have time for questions. The usual procedure, please type your questions into Slido, and then I will read it aloud here. Meanwhile, I start with a question. Where are the weak points, or how does a data set should look like that it's very good for your approach, and what kind of data sets would be the complicated cases where you probably want to avoid?
No, that's a very, very good question. So one of the limitations of this approach, as you can imagine, is that the data set has to have many smooth regions, because otherwise it will not work, right? So we rely on having, like here, for example, there's a wide region where the mesh and the attributes are just flat. So here, the wavelet compression will work really, really well. So if your data set has like super high frequency, yeah, it's probably not the best approach. So you have to be careful in terms of choosing what to use. Great question.
Further questions? If not, I have to continue. I don't know if this is good for you or not. That's your approach is pretty much going toward geological data. How general is it? Is it possible to straight apply to completely other kinds of data, or is it pretty much tuned to this particular kind of geological data?
We can probably extend it to data sets where the mesh and attributes have kind of a very structured, or are very structured. Because for us, one of the challenges was trying to come up with a representation where we can process the mesh and attributes together or jointly. So if it's unstructured, I can imagine it's probably harder. But yeah, if you have more structured data, maybe you can apply this technique.
Okay, thank you very much. Further questions from the audience, from the world, from the internet, from somewhere? This is not the case. Then thanks a lot for the presentation. And we come to the second talk. This is also an in-person presentation. Is the speaker up? Yes, go ahead. So the title is Cosmovis, an interactive visual analysis tool for exploring hydrodynamic cosmological simulations, and the authors are David Abramov, Josef Burchett, Oscar L. Cameron Hummels, Xavier Prochaska, and Angus Forges. Let's go.
Thank you. Yeah, I'm David. I'm a PhD candidate at UC Santa Cruz, and I've created this project Cosmovis in collaboration with astronomers at New Mexico State University, Caltech, and UC Santa Cruz. So what is Cosmovis? It's this web application we created where we can explore large-scale hydrodynamic cosmological simulation data sets. So what does it do? What is it? It's an interactive data visualization where we can load and render these big box cosmological simulations in the web browser. So we can display gas, dark matter, and star particles within a unified framework. We can also probe these simulated universes with what we call skewers to generate synthetic spectra. So this is an example of a user interaction with Cosmovis. So we have on the left a 12 megaparsec Eagle simulation box, and the user has clicked and placed a skewer within the simulation. Cosmovis allows you to switch between different field properties that are in the simulation. So here on the right, I show density, temperature, metallicity with different color scales. So it's the same slice, and we have the same line of sight piecing through it, but we can look at different properties along that line of sight, which is shown in the graph below each of these frames. And these correspond to the way that astronomers actually measure the universe, so we can make apples-to-apples comparisons between simulations and observations. So let me go deeper into the cosmological background and why this is relevant and why it's interesting. So astronomers create these cosmological simulations to look at the formation of the universe from the Big Bang all the way to the present day. So right after the Big Bang, there's gas and material in the universe, but no stars have formed yet. So it's called the dark ages of the universe. Then we start to see more stars start to form, galaxies emerge. Over time, galaxies evolve, they combine, coalesce. And then at present day, we can look back into the universe and observe galaxies at different time points. So astronomers simulate the universe using what they've called simulation stew. So they start off with some initial conditions like dark energy, dark matter, gravity, gas cooling rates, star formation rates, black holes, hydrodynamics, initial conditions. And they let these simulations run from the start of the universe until present day. And there's all sorts of different simulation suites out there, like Illustris TNG, Eagle, Simba. They're all generally modeling the same thing, right? The formation of the universe, but where differences arise are in the numerical methods and the tuning of uncertain parameters to observations that leads to different results in the simulations. So the traditional pipeline for working with this kind of simulation data is a little complicated. You have to acquire the simulation data. These can be terabytes in size. You need a powerful enough computer to open up these simulations. Then you need to query the simulations for interesting regions, so generally writing Python scripting to look up different parameters. And it's not exactly straightforward to identify like what's an interesting region to study without actually looking at the data. So with CosmoViz, we aim to create a tool where we can access multiple different types of data sets, perform exploratory analysis on those different simulations, and then extract these science-grade synthetic spectra that can be directly compared to observations of the universe. So that leads me to a set of analysis tasks that we developed with our team of astronomers. So the first task is to identify structural patterns in simulation data. Our second task is to simulate the absorption line spectroscopy. Task 3 is to connect the intergalactic medium and circumgalactic medium observables to gas physical conditions. And task 4 is to compare simulation results. So let me go a little more in detail in these tasks. So task 1 is to visually identify structural patterns in simulation data. So if you're just looking at the raw data, not an image, it might not be too clear where an outflow is or a galaxy or a filament is, but in the visualization you can clearly see like these entropy bubbles and accretion shocks as galaxies expand. You can see filaments where material coalesces, galaxies or clusters of galaxies, dense regions like walls and sheets, and also voids where there isn't any material. So here we can see galaxies with some star particles in the center, and we can identify some outflows. We can switch between different fields. So here we have temperature, density, metallicity, mass, and we can see the large-scale structure of the universe. So here, like these different filaments are readily apparent. And we can also identify like really interesting sheet regions where we have lots of filaments combining in one region. So we have lots of different dense clusters of galaxies which might have interesting properties worth exploring. So it's one thing to just visualize this data. It's another thing to analyze it. So task 2 is to simulate absorption line spectroscopy, which is the primary method astronomers use to measure the universe. And this data provides information about different physical quantities along a line of sight, such as column densities, metal abundances, and then you can also interpolate physical properties such as temperature, density, metallicity, entropy. The issue with observations is that real galaxies usually have very low sampling. Like at most, you might have one spectra for a galaxy, but with CosmoViz, we can easily probe features with many sight lines by interactively placing them. So what are these absorption spectra? So generally an astronomer will point their telescope, such as the Hubble Space Telescope, at a bright point somewhere out in space, usually a distant quasar, which is a supermassive black hole emitting light towards the Earth. That light travels through the universe, and the intervening material will show up as a fingerprint on the spectrum, indicating what kind of elements are there out in the cosmic web. A tool we worked on before worked with observation data where we projected galaxies into a 3D space. We had these observation spectra, and we wanted to look at the impact nearby galaxies have on the spectra. So we extend this in CosmoViz to not work with observation data, but the same analogy in the simulation, so we can start to compare simulations to the way astronomers actually observe the universe. So that leads me to task 3. What's some of like the science happening here? So we can connect the intergalactic medium and circumgalactic medium observables to gas physical conditions. So these column densities are measurable in actual spectra in the real universe, but thermodynamic quantities such as temperature and density must be inferred from those measurements with sophisticated modeling. So physical properties actually have a high uncertainty from observations, but are less obfuscated in the simulation data, since all of that data is stored within the simulation. So the intergalactic media, this is the large-scale structure of the universe where we can see the filaments and the voids. Here, for example, it's like a background quasar. We have a distant galaxy in between, and there's some absorption pattern that tells us what kind of metals are within that material. We can also study the circumgalactic medium this way too, where we have a background light source like a quasar, and there's an intervening galaxy, and we can study some gas properties about that galaxy. But like I said, in the universe, usually we only have at most like one spectra for a galaxy. So in this case, like it's only piercing the edge of the galaxy, and we're missing information about this recycling gas, the outflows, some accreting gas. But in Cosmoviz, what's great about the simulations and interactively placing the skewers is we can place as many as we want and get a lot more information that might be lost just from doing observations. So task 4 is comparing simulation results. So we can analyze selected features of a single simulation data set. We can compare simulations to empirical data. We can compare different snapshots within a single simulation. So we can look at early universe of the simulation to like present day in the simulation. Or we can look across different simulations entirely. So an example of something you might want to study is like some poorly understood physical concepts, such as the conditions underlying star-forming regions and quenched regions with large star formation rate. And it kind of goes through this cycle where you make observations, you model and simulate what you're observing, and then you see, does the simulation compare to the real universe? Are we getting similar types of results? How do simulations compare to each other? And it's just like a process of refining the simulations and coming up with a better model of how the universe works. So with Cosmoviz, we wanted to make it as data agnostic as possible, where we could load in like any type of cosmological simulation. So here we have a few boxes from the Eagle suite, as well as the TNG Illustris data sets. So how do we do this? The architecture of Cosmoviz is we have a web front end powered by Three.js for an interactive 3D visualization, as well as D3.js for 2D static plots. The front end talks to a cloud computing backend using Flask and Socket.io, where on the back end, on the cloud somewhere, we have persistent storage holding the simulation snapshots, and then we have some computing resources running Python with packages such as YT and Trident, which produce the skewer sightline data, such as the column densities, physical properties, synthetic spectra. So we do some data compression for the visualization. So the gas in the simulations come as particles, but then we turn it into voxelized grids, which we can then turn into a volume rendering that's continuous. And then we embed star particles within the volume so we can still see like where the dense parts of the simulation are. So we use YT to load and voxelize the data sets as well as produce the spectra. We have a user interface where you can select data, go through different layers and adjust the color scale, query galaxies, and plot the spectra. So ongoing future work, we're working on animating the temporal evolution of these simulations and then working on galaxy queries and zoom-ins. So here's an animation of what I've been working on where we can animate the evolution of the universe. And then we've also been working on a galaxy query tool where we can zoom in on individual galaxies within the simulation and do the same kind of interactions. Ready? Yeah.
Thanks a lot. Thanks for the presentation. All right, we have a few questions. Alex Bock is asking, how would you want to adapt your tool to account for non-straight skewers? In the real world, the measurement rays are curved due to gravitational lensing. Hard question.
Yeah, I didn't get the whole question.
Sorry?
I didn't hear that.
Maybe you can read it.
Oh, okay.
The acoustics here is really bad and it's really hard, so sometimes it's better just to read the questions.
Okay. So we're using the Trident package to create the synthetic skewers. So it's more so up to the underlying code that we're using to process the data. So we're using an existing package. Our collaborator Cameron Hummels at Caltech, he produced the Trident package. But that's not my specialty.
All right. Here we have a further question. Marco Agus, great work. Did you consider using topological data analysis for the identification of structural patterns?
Yeah, we did think about it and consider it, but we thought for this tool, some of the features we're interested in looking at are like readily available, like to just visually identify, especially once you tweak certain parameters, like you can control the density opacity, so you can isolate denser regions, you can isolate specific temperature regimes, et cetera, in the visualization. So we thought that handled that kind of analysis.
All right, we have a few more questions. Maybe one last one, then we have to go offline. Where does the data sit? What is the backend? What data set size can you process? Both particles and AMR data sets?
Yeah, so there's two parts of the data set. So we pre-process what gets visualized, and this is hosted as static files on the web server, and that's what the client side renders. Also on the server, we have the full simulation snapshots. So this is used for generating the synthetic spectra. Since these simulations are quite large, we figured it's better to pre-process some files for visualization, and then that's happened pre-processed offline, and then in real time we can process the skewers using the full simulation data. And that way we avoid having to send the full simulation to the client side.
All right, thank you very much. The further questions I think we have to take offline because we're running out of time. Thanks a lot for our presentation. We're coming to the third paper. This is a virtual presentation, and the title is Dynamic Mode Decomposition for Large-Scale Coherent Structural Extraction in Shear Flows. And the authors are Duong Nguyen, Panru Wu, Rudolfo Ostia-Monico, and Guoning Cheng.
Hi, I'm Duong Nguyen from the University of Houston, and on behalf of my co-authors, I'm here today to present our paper, Dynamic Mode Decomposition for Large-Scale Coherent Structural Extraction in Shear Flows. Let me start with a quick introduction about the shear flows. A shear flow is fluid motion created between two surfaces which have different velocity. There are two types of shear flows. The first one is called Taylor coef. The second one is wave lift. The Taylor coef is controlled by a solid body rotation omega. Wave lift can be thought as a variation of the Taylor coef flow, but instead of using the rotation, it uses a sinusoidal body force. The most important features that domain experts look for from shear flows are coherent structure. In terms of existing work, there are many techniques in the literature to extract coherent structure. The most prominent type of the coherent structure are vortexes. For the vortex detection, two main approaches, the region-based and line-based methods, are local and only good at capturing the small-scale structure. Another set of the methods use FTLE to extract the Lagrangian coherent structure, but it does not provide the scale information. The topology-based methods are popular for steady flow analysis. However, they do not work well with the turbulence flow. The non-topology-based methods like Fourier transform or convolution kernel smoothing also do not work well with the shear flow due to the need of setting up thresholds. In our work, we rely on the methods called dynamic mode decomposition, or DMD. This is a spatial temporal decomposition of time-dependent data into a set of spectrum components called DMD modes. It's a parameter-free technique. DMD modes encode spatial feature, and each mode is associated with a time dynamic. This time dynamics or time evolution describe the temporal behavior of the DMD modes. We can characterize DMD modes based on their time evolution speed. For example, in this illustration, the top mode is slower than second mode because its time evolution has larger periods or lower frequency. There is an extension of standard DMD, which is called multi-resolution DMD or MRDMD. MRDMD is a recursive process which tries to separate slow mode from the data. Here is a description of the MRDMD algorithm. First, we apply the standard DMD to the data, then find the fast and slow modes. We subtract the reconstructed field based on the slow modes from the data. The remaining data containing fast mode and is split in half. We repeat the whole procedure for each half of the data. There are a couple of the characteristics that we think DMD can be used to extract the large-scale structure for shear flow. First, DMD mode can be characterized by how fast or how slow they move. You can see that both slow modes and the large-scale structure have the slow temporal behavior. Secondly, DMD modes can extract the flow structure, which evolves linearly. This characteristic coincides with the linear characteristic of the large-scale structure in shear flow. If you look at the example I'm showing here, we have the original velocity field on the left, subtract the field reconstructed by the slow DMD mode in the middle, and get the remaining data on the right. The slow DMD mode indeed reveals large-scale vortex, which is highlighted by the black circles, and the slow mode leaves out the small-scale structure, which are in the small red circle in the fast mode. And the question is, does every slow DMD mode is useful for the large-scale coherence extraction? We found that only the slowest mode can capture the large-scale structure. These examples show different slowest mode, 3 levels in the left, and the multiple slow mode of the first level in the right. As you can see, the structure can be observed only in the slow mode. The above observation lead to our main contribution. We propose to utilize MRDMD for the large-scale coherent structural extraction task. MRDMD has not been applied to the 3D data due to the performance limitation. To address this issue, we provide a fast GPU implementation to perform the experiments with the 3D shear flow. We evaluate the methods comprehensively, which means we compare the result of DMD with the most commonly used methods for the coherent structure extraction. We also provide the empirical-based insights regarding the application of DMD on other types of flow. Next, we briefly describe how DMD is computed. Basically, DMD tries to find the dominant eigenvalue and eigenvector of the best linear approximation that sends data from its current state to next state. The linear approximation is presented by the matrix A. So DMD modes actually are the eigenvector of A. The eigenvalues are used to compute the temporal dynamics. Note that the eigenvalues are complex numbers, and one way to characterize slow fast mode is based on the distance of the eigenvalues to the origin in the complex circle. Closer to origin means slower. The input data or the X matrix here are very tall and thin. Each column is the flow data at the given time, which is arranged in the vector format. This means that the number of the rows is significantly larger than the number of the columns. So it's nearly impossible to compute the matrix A directly. Instead of compute the matrix A directly, we can perform the following transformation. First, we multiply both sides with the inverse of H1. We got A equal to H1 inverse. Next, we apply SVD or singular value decomposition on the inverse of H1 to get V sigma in view. Put use and use inverse to the two ends of the equation. We have this equation. We denote A title to present the left part of the new equation, and this is proof that A title is not only has similar sign as X1, but also has the same eigenvalue as A. Instead of compute A, we now just need to compute A title. The heaviest computation step is the singular value decomposition of the X1 inverse. To speed up the computation of SVD for the large thin matrix, we provide CUDA-based implementation based on the QR decomposition. QR decomposition decomposes matrix A into a product of two matrices, Q and R. Q is an orthogonal matrix and R is upper triangle matrix. The high-level idea of the parallel QR computation is that we first split data into smaller chunks, let's say from 1 to n. Then we perform QR decomposition for each chunk. We then combine R1 to Rn to create R prime, which has smaller size, and then perform another round of QR decomposition on R prime to get the final R. The final Q is the combinations of Q in the small chunks. We evaluate our implementation on 10 artificial flow datasets with the size increased from 17 MB to 2.3 GB. Here are the plots showing the performance. The GPU-based implementation significantly reduced the running time, making DMD feasible to the last flow dataset. We also evaluate the relative errors to make sure the implementation are correct. Here's the detailed performance of GPU implementation on the actual shear flow data. Let's look at the result of the MRDMD on the 3D Taylor graph flows and compare with the commonly used methods, convolution, kernel smoothing. Here we use streamline to depict the large-scale structure. As you can see, the DMD methods clearly reveal better shape and position of the large-scale structure. These DMD results also align with the finding in the previous work as shown in C. However, DMD require no parameter selection. This shows the visualization result of the 3D relief flow. The original flow in the left does not show any meaningful pattern. The last structures, which are vortex, are clearly shown by the streamline in the slowest mode. Again, the last structures are only observed in slowest mode, not in the other mode. This is a complete 3D view of the large-scale structure depicted by streamline for the relief flow. We also use pathline to demonstrate the shape of the current structure. The pathline in B comes from the original field, which is very turbulent. The pathline in C shows a very clean vortex shape, which is the last structure existing in the relief flow. We also compare DMD with proper orthogonal decomposition of POD and time-moving average methods. More details can be found in the paper. Here is a comparison with POD. Both POD and DMD can reveal similar shape of the structure, but POD cannot characterize the temporal behavior of the structure. The large structures move slowly and do not change the time evolution frequently. This behavior can captured by DMD, but not with the POD, where the time coefficients change abruptly. Slowest mode can reveal the large structure in the shear flows. The next question is, can we use it for the other type of flows? The answer is not a way. We are seeing here the result of the MRDMD on a 2D cross-section of the vortex ring. This flow has the main vortex moving from the center, hit the wall, and break down into two smaller vortexes. The slowest DMD mode, so in C, clearly does not capture this behavior. We have to combine multiple level of the MRDMD to capture this behavior, as shown by picture E. To conclude, we introduce to the visualization community a large-scale coherent structural identification framework for shear flows based on dynamic mode decomposition. In particular, we saw that the slowest DMD mode can characterize the coherent structure that have slow temporal evolution. There are few limitations that we aim to improve. First, DMD is biased to the structure that are characterized by the attributes used for DMD computation. In this work is velocity field. Second, we only focus on the slowest mode in the first level. Investigating the submode in the different level are also promising to characterize the hierarchical behavior of the flow feature. Thank you.
Thank you very much. All right, we can see you, and hopefully you can hear us. Hello.
Yes, can you hear me?
Wonderful. Let's get started. Are there questions? We have actually time for one short question, and don't any questions in the chat yet, so I ask a question. You have shown in a pretty nice way that DMD works pretty well for shear flow, and for other flows, depends. Sometimes yes, sometimes no. Do you have more insight why the technique is so good for shear flows? What is special with shear flows that DMD is especially useful for this?
Yeah, so this is a very good question. So actually, one of the characteristics that we mentioned in paper is kind of like the linear transition of the large-scale structure existing in shear flow. So the lowest mode of DMDs work very well for the kind of linear temporal behavior of the structure. So I think for we haven't found every flow yet, but we think that in addition to shear flow, if we have other type flow that have the linear temporal behavior, yeah, I think MRDMD can work as well.
All right, thank you very much. If there are further questions, let's take them offline. And thanks again to the speaker. And Let's go to the next presentation, which is a virtual presentation as well, a comparison of spatial temporal visualization for 3D urban analytics. And your authors are Roberta Mota, Fabio Miranda, Julio Daniel Silva, Marius Horga, Marcos Lage, Luis Seferio, Usman Rasa Alim, Eo Chalin, and Jan Ferreira. Let's get started.
Hello everyone, thank you for attending this presentation. My name is Roberta Mota. I'm a PhD candidate at the University of Calgary. In this video, I'll be presenting a work involving a comparison of spatial temporal visualizations for the area of 3D urban analytics. Our work was motivated by the fact that there has been an increasing availability of time-varying data defined on 3D building surfaces. And analysts from the urban domain typically rely on visualization to perform spatial temporal analysis on this data. So our goal was to investigate the question of how effective visualizations are at supporting spatial temporal data analysis in 3D building surfaces. This investigation led to 3 outcomes: a task characterization as a list of representative spatial temporal tasks for 3D urban visualizations, a comparative quantitative study, and an informal qualitative evaluation with practitioners from the 3D urban domain. Today I'll be presenting about our quantitative study, but you can find information about the 2 other contributions in our paper. By reviewing the literature, we learned about 4 representative spatial temporal visual designs coming from either 2D information visualization and designs coming from 3D scientific visualizations. We also classified 3D urban visualizations published over the last 10 years, selected 34 papers, and learned what are the designs that recent 3D urban visualizations most typically use. We then selected these common designs for a comparative study. For this study, we generated 2 medium-density 3D city models. The temporal attribute was the sunlight access to the building facades with added noise to increase data variability and had 4 time steps. For the visualizations, we extended the 4 representative visual designs previously learned from the literature to the context of 3D urban models. Temporal juxtaposition encodes the temporal attribute using a sequential color map. It displays only one data instance at a time. Spatial juxtaposition also uses color encoding but arranges all time instances in a 2x2 grid layout with 4 viewports. Embedded view displays all time instances on a bar chart that is embedded in the building surface. In the chart, the attribute value is encoded as the position along the y-axis, and the time instance is encoded along the x-axis. Linked view also displays all data instances on a bar chart, but the chart is arranged on the right side of the screen. These 4 visualizations can be classified into 2 major groups. Plot-based visualizations visually encode the attribute as the position along a common scale of an abstract plot, and color-coded visualizations map the attribute to the color visual channel of the building grid cells. For the purpose of the study, the visualization supported interactivity. In this trial example, 2 partially occluded and fairly distant facades are considered. And as you can see in the video, the user could navigate the camera and could also create, move, and delete regions along the building facades. The concept of region will be explained in the next slide that talks about the study tasks. For this study, our base task was to search for a facade region with extreme value over a certain time period, which translate to questions such as, what's the facade region with maximum value in time step 1? Or what's the facade region with the minimum value between T2 and T4? A facade is one side of the building, and the facade considered in its trial example is highlighted in green. And we define the region as a compound area of 2x2 grid cells along the building facade. For example, in this image, you can see 2 regions. And given that a region is composed of 4 cells, the region's value is the average of the 4 cell values composing that region. So to perform the base task of searching for a region with extreme value, one has to mentally compute the average value of the regions based on either color or position encoding. From the base task, we created 12 task variations and divided them into groups of lower and higher complexity. The tasks were also classified according to 4 conditions that may increase the complexity of a visualization task. For example, increasing the number of time instances may increase task complexity. So for this condition, tasks that consider a single time step have lower complexity than those considering a time interval. Increasing the number of spatial instances may also increase task complexity. So single facade location tasks consider a facade from only one building compared to multiple facade location tasks, which consider two facades from different buildings. Camera navigation may also increase task complexity, so single viewpoint tasks do not require camera navigation because these tasks consider unoccluded facades that can be entirely captured from a single point of view, compared to multiple viewpoint tasks which do require continuous camera navigation because these tasks consider partially occluded facades in either one or two fairly distant buildings. And for the viewing angle condition, single orientation tasks consider facades facing a single view direction, and multi-orientation tasks consider facades facing orthogonal directions. The study used a between subjects design with 32 participants. Each study session had 3 parts: an introduction to the experiment and 5 training trials, 12 main trials, and a questionnaire where participants shared the benefits, difficulties, and their strategies when using the visualization. The video shows an example of a trial. On the top left corner, a text box shows the task question and all existing regions at any given time. And by selecting a region on the list and clicking the next button, the user submits that region as the task answer. For the study results, the first question was, is there a difference in efficiency between the 4 visual designs? And by looking at the average error values, we found that participants were considerably more accurate when using plot-based visualizations compared to color-coded visualizations. And by looking at the pairwise comparison between the visualizations, we found no clear difference in accuracy between embedded view and linked view. Based on participants' comments in the questionnaire, we believe this result was caused by the fact that participants could not perceive minor variability in the data through color encoding. When we looked at time performance, we found the opposite case, as color-coded visualizations were considerably faster than plot-based visualizations, with no clear difference in completion time between temporal and spatial juxtaposition. Based on participants' comments and our own observations, we believe that plot-based visualizations were slower as they require spatially scanning the building facades. And we observed that participants spent significant time scanning the facades not only to identify attribute values, but also looking at minor differences in these values to verify their final choices and trying to access the values in partially occluded areas. The second research question was, for each visual design, is there a difference in efficiency with an increasing task complexity? We found that plot-based visualizations scale better than color-coded visualizations, given an increasing number of time instances. By looking at increasing task completion time, we observed that there was no significant increase when using plot-based visualizations. But the same was not true for spatially and temporally juxtaposed visualizations. We believe this result is because plot-based visualizations collate all temporal values in close proximity in each individual bar chart. So increasing the number of time instances does not add significant cognitive load to participants. When looking at increasing task error due to increased complexity, we found that plot-based visualizations generally scale better than color-coded visualizations. Linked view did not have significant error increase for any of the 4 task conditions. And embedded view showed a similar behavior, but with a little error increase for the camera navigation condition. And we believe that this was caused by the fact that by the continuous context switch while navigating the camera. But the same was not true for color-coded visualizations, where participants had higher error rates and in more task conditions. We believe this result is aligned to our previous takeaway that plot-based visualizations allowed participants to better discriminate variability in the data, irrespective of the number of time instances, spatial instances, and viewing angle. Based on the study findings, we draw recommendations of visual designs that were most effective considering all tasks collectively, and designs that were most effective given increasing task complexity conditions. From this table, we can also observe that plot-based visualizations more often preserve efficiency compared to color-coded ones, considering the different task complexity conditions used in the study. To conclude this presentation, we reiterate the research question investigated in our work and the 3 outcomes from this investigation. We focus today on presenting our quantitative study, but you can find information on our paper about the 2 other contributions. For future work, some ideas include to tackle occlusion by considering a combination of our spatial temporal designs with the occlusion designs. Another idea is to investigate how to incorporate these visualizations given buildings with irregular geometry. Additionally, because our study considered only a few tasks taken from our task characterization, future work could cover a wider spectrum of tasks. And lastly, our study provided insights on how well visualizations scale considering only a few spatial and temporal instances. So future work could focus on scalability and investigate a larger number of instances in both space and time.
Thank you very much, Roberta. I hope that you can hear and see us, because we used to have a question that already disappeared. Then I might ask you a question. Talking about the different representatives for visual designs, you have basically chosen 4 of them. How complete is this set? Might have been possible to think about others, or do you expect that other visual designs may pop up in future? How unique was it to select exactly those 4?
Yeah, that's a good question. Thank you. So the way that we handled the selection of representative visualization designs was through a literature review. So we looked at a taxonomy for 2D geographical visualizations coming from information visualization, and also a taxonomy of visualization designs for in scientific visualization for 4D visualizations. And from the information visualization side, we found linked view and embedded views were few common visualization designs using information visualization. And for scientific visualizations, we found 4 different visualization designs. We found spatial juxtaposition, temporal juxtaposition, encoding, explicit encoding, and superimposition. And on the paper, you can find more information on the paper for our reasoning for selecting only spatial juxtaposition and temporal juxtaposition. But in summary, the reason why we decided to go with spatial and temporal juxtaposition was because when we reviewed the 3D urban visualization systems for the last 10 years, we found that these two visualization designs, spatial juxtaposition, temporal juxtaposition, was the most commonly used. And we found very few designs using explicit encoding and superimposition. We also argue in our paper, and you can read more information in our paper, we also argue that superimposition has to be very careful with the design because it can lead to clutter very easily. So we try to avoid having these design challenge in our paper that could bias the study results. And with explicit encoding, the way that this design deals with the visualization is you don't show each data instance at a time. You will create a composite visual data, for example, with the intersection, with the addition or subtraction from different data instances, and then you show this composite measure. And in our study, we didn't want that. We wanted to show each data instance at a time during the study. So yeah, so these were the 2 main factors why I decided to go with the spatial juxtaposition, temporal juxtaposition, embedded and linked view.
All right, thank you very much. So thanks again for the presentation and answering the questions. And we have to move on to the next presentation. This is in person again. It's called EPIMOB, Interactive Visual Analysis of Citywide Human Mobility Restrictions for Epidemic Control. And the authors are Changwang Yang, Xingwen Zhang, Sipel Fan, Renhei Yang, Kwangyung Cheng, Chuang Song, and Rusuyo Shibasaki.
Okay, shall I start? Okay. Hello, everyone. I'm Chang Yang from the University of Tokyo. And today, I want to introduce a simulator. This simulator is designed during the COVID-19, and I want to introduce how visualization play an important role in our simulation design. First, I will give a brief introduction. The research context is, as we all know, various countermeasures such as self-contained travel restriction or mask wearing has been implemented during the COVID-19. And it's important for policymakers to evaluate the effects of the countermeasures quickly so as to make rational and scientific measures. And one of the main routes is simulation, which means simulating the effectiveness of the intervention policies. For example, the Cabinet Office of Japan launched the COVID-19 AI and simulation project. However, the policy searching process is tedious and inefficient, because it requiring substantial programming efforts and for the modeling and the results analysis. And also, it's always facing a large state space when we explore when and where forward policies. So visualization can help us. And currently, there are some work. These simulators are designed based on interactive simulation and analysis of intervention policies. And they convert the complexity coding work to this kind of easy-to-use UI. So they are good visualization and interaction design, and also enhancing the efficiency of policy exploration. And it makes being accessible by a broader set of users. However, they just simulating at county and higher spatial scale, which means they simplify the city-wide scenarios. They just treated the city as a minimum implementation unit, so you can't get the detail. So simulators towards citywide fine-grained epidemic control are still blank. However, the citywide fine-grained epidemic control could be a more proper route for restraining spread when maintaining the normal livelihood. For example, the left side, we just lock down the whole area. This is very common during the very early stage of COVID-19. But if we could just lock down some areas and also telecomputing on some areas, it will be a better choice. So our design targeter is designing a simulator for citywide fine-grained epidemic control and aiming to simplify the policy searching process in city scale. And currently, due to the time and data limit, IPMOB merely support mobility-related policies. And so there are some challenges. The first one is when and where for what policies in citywide. And you need to handle the right side differently with the left side. You have to handle the local control policies. There's no clear administrative boundaries. And also you need to consider the complex intra-city features, such like the population density, the internal functions. There's no existing solution for this. So we use the visualization to help us do this. We devised the interactive policy exploration and setting module to do this. So this is the first part. And the second part is how to accommodate such complex policies. Because the policies have different types, different intensities, even spatial time scope of the restrictions are varying. So and also sometimes users need to perform multiple types of policies simultaneously. And this side, we use the trajectory-based SER model. And here is our module. And giving the raw trajectory data, we first extract the users who was affected by the trajectory and then generate a new trajectory data set. So we have many restricted mobility, and then we directly feed it to the simulation model. So any model is OK. So here we use a trajectory-based SER model. And the last one is deeper understanding of the simulation result. We do not just want an infection curve, and we want to understand the fine-grained secondary effects, like the new infection hotspots and the new hub node. So today I will briefly introduce these two parts. It's quite related with visualization. So this is a UI overview. And this is for policy setting, a lot of spatial views. And after you finish the setting, you can get the results. And by clicking the in-depth analysis, you can perform in-depth analysis on the results. So this is a view. The first view is for regional lockdown. And each marker covers some spatial range, and it depicts how many people infected here. And you can directly select some regions and lock it down, and then select lockdown time and start time and which regions. So this is first view, and the second view is called telecomputing view. It's a heat map to visualize the workplaces of individuals. And you can, sorry. And so by this way, you can select which district to perform in telecomputing, and you can ask our system to how many people stay at home. So this is the percentage, and how long this policy implemented. So, and during simulation, the people satisfied the rules will work from home. And the last one is just a scatter plot to display the POI distribution, and the user can directly draw the markers on map to select where to perform screening. And during the policy implementation, all the people passing the marker covering regions will accepting a screening. If detected, they will be isolated later. And now after, if you click the simulation, you will get a result. And you can select a multi-result at the same time to compare which one is the best. And also, so the secondary effect is very important. So we devised this view to analyze the secondary effect from the perspective of spatial transmission based on the flow map blue, this library. And the first part is a map component to display the spatial transmission network. We collected all the initial infection location and the secondary propagation location to construct this network. The bidirection of the edge and encode the direction of the spatial diffusion. And another important part is a filter component to explore the cross-region propagation patterns. Because as we all know, this is a network. For each node, it had many input and many output. So someone is very important. So we set a threshold to help user filter this. Yeah. And the last part is a tracing panel to explore the local infection patterns. And each bar here represents a region. And the blue bar and red bar encode the proportion of the two infection types. For example, region B, this people is infected in region B, X, and he moved to region A and infect Y in region A. So, and also Y also transfer the disease to Z in region A. So there are two kinds of infections. The first type is input propagation, and the X infected in region B transferred to the people in region A, and another type is inner propagation. So we calculate the percentage of these two kinds of infection to represent a region, so we can know the type of each region. So next, the case study, I will show how visualization in FMOB helps us to explore and understand the policies. And here are the basic settings. We use the trajectory data, real-world trajectory data in 2012, 1 month data, and the spatial range is the Greater Tokyo area. And we use 30,000 people, real-world people trajectory, and the model is a SER model. The trajectory is a SER model, and all the parameters are referenced to medical papers. Yeah. So the first one is exploring the effect of different lockdown. And the first one, we just locked down the very severe regions, Shinjuku and Shibuya and Ginza in Japan. And the right side is the central part, whole central part of Tokyo. And we can find that this is an infection curve with 4 different start time. And we can find the sooner the policy was launched, the more significant the effect. It's very intuitive. And another is the regional lockdown does not appear to fully contain the outbreak. If you just apply regional lockdown, if just someone move out to this lockdown region, so it will continue outbreak. And here's the network view, and you can see compare with the no intervention, lockdown on central part of Tokyo will create a new epidemic center, which is epidemic, which is Yokohama, and we can see that Yokohama will become the new epidemic center, and Yokohama, as you can see the highlight, you can find the Yokohama will contribute to more than half the important cases in surrounding regions. So, but this is just a simulation. In fact, Japan do not lock down the central part. And the second case is exploring effect of large-scale telecomputing. And the left side also is a no policy, and the right side is on the whole telecomputing on the Greater Tokyo area, and we can find that the infection hotspots shift to the nearby regions. These regions are the residential area. residential area of Japan. So this is aligned with the news that household infection rate in Japan area with the most common routes of infection in Tokyo. And the last case is for large-scale lockdown. We can find the large-scale lockdown is the most effective one. And yeah, large-scale screening and isolation because it broke the transmission network. And most of the infection are local propagation. So this here is a summary. We explore site and simulator various mobility restriction policy at state scale and measure and compare the analysis of the effectiveness of policies. Currently, just 3 policies are supported. And in the future, we will integrate economic cost and automatic parameter calibration. Yeah, and all the modules can be customized by users themselves. So thank you for listening.
Thank you very much for the presentation. We have time for one question, and the question is already here. Interesting talk. What were the decisions behind various color schemes you used in your layout? Are they somehow connected between the views?
This question, yeah, this is a good question. We haven't considered the color schema. We just use this color schema using in the library inherently. Yeah.
All right, then let's thank the speaker again for the presentation. And we come to the last presentation in the session. This is a virtual presentation. And it's called On-Tube Attribute Visualization for Multivariate Trajectory Data. And the authors are Benjamin Russich, David Groß, Raimo Daxelt, and Stefan Gumhold from Dresden University. And Benjamin gives the talk.
Hello, my name is Benjamin Russich, and I will be presenting our work on on-tube visualization on behalf of my co-authors. First, let me introduce our work with a little bit of use case-driven motivation. If you were to visualize some 3D line data, say streamlines of a flow field as tubes, then in ParaView you could come up with an initial solution like this. You might map 1 or 2 additional attributes to tube color and maybe radius, and perhaps use some type of glyph to indicate flow direction. If you need the evolution of many attributes, then the possibility of using abstract views on the data exists, but you lose the spatial intuition your 3D visualization afforded to you. Techniques that enable tubes or ribbons to carry additional attributes exist, of course, but either they allow for just 1 or 2 of them, or they limit the spatial complexity that can be visualized effectively. And of course, there are many sources of trajectory data, some of which come with potentially dozens of attributes. So the question we asked ourselves is, can we have both? Can we retain the spatial intuition afforded by tubes and at the same time visualize the evolution of many additional attributes without resorting to additional views? And as an answer to this question, we came up with on-tube visualization. The core idea is to retain tubes as the primary visualization primitive with all their favorable properties like independence of viewing angle or the fact that they sometimes are a direct non-abstract representation of the objects that form the line data, and utilize their surface as a canvas for visualizations that can be more intricate than simple directional arrows or modulated patterns. With this, we want to enable analysts to at least locally identify trends, correlations, divergences, and so on of non-spatial attributes with the spatial evolution of the data. Of course, this is not entirely a straightforward endeavor, and it comes with many challenges. Most obviously, the curved surface of the tube and also the curve of the trajectory itself induce distortions on things drawn onto them. Embedding 2D visualizations in 3D space also induces perspective distortion. Then there's the problem of canvas size and how well things can be recognized from further away. Line data can, of course, originate from many domains with a multitude of attribute types, which could be sampled continuously, irregularly, or even be discrete events rather than values. And tying into this is the fact that for some fields, line data can become extremely large, with millions of position samples alone raising concerns about real-time capability. Naturally, we could not address all issues yet, so right now we cannot do anything about perspective distortions, so viewing the side of a tube head-on will always work best. Our visualizations do become unreadable when far away from the data, so users will have to navigate to areas of interest in order to see the additional attributes visualized. We do not address these problems right now, and our work is focused mainly on the technical groundwork that enables this concept to begin with. So to make precise drawing onto tubes possible, we propose a parameterization that behaves very similarly to a view-aligned ribbon, reducing distortion and enabling precise sample placement by trajectory arc length. To support as many types of attributes as possible, we propose a procedural approach to glyphs and plots that is based on signed distance functions. So anything that can be expressed in terms of an SDF is directly supported. However, since we're working in texture space, our approach works best for scalars and completely abstract things like events. Finally, and perhaps most importantly, we engineered a high-performance deferred shading pipeline that allows for drawing millions of complex glyphs with minimal performance impact onto a high-fidelity tube surface. So now I'm going to give a rundown of the building blocks of our technique, and I'll start with listing the basic design key points. Fundamentally, on-tube visualizations are a stacking of discrete or continuous mappings, so in other words, plots and glyphs, organized in individually configurable layers, plus optionally a configurable reference grid. Each layer can contain a single glyph or plot type and manages attribute mappings, windowing, and other parameters. Of course, we want the on-tube visualization to always face the viewer to reduce the need for navigation, and we accomplish this by making the surface parameterization view adaptive. That way, placing a glyph simply means deciding where along the trajectory the local drawing coordinate system of a glyph should originate, and the parameterization takes care of the rest. The center point of that coordinate system decides where the mapped attributes are being sampled, and in order to make sure that the coordinates are meaningful for drawing things, we need the arc length of the tube axis. The glyphs and plots themselves are implemented as signed distance functions, meaning that during shading we decide based on the function value whether a surface point is outside, inside, or on the outline of the glyph or plot. SDFs allow us to basically describe any shape by means of composition, and to the right you can see a selection of the SDFs we tested. Among them, implementations of star coordinates, line plots, and temporal heat maps. As a particularly illustrative example for the procedural nature of these glyphs, take the implementation of the sign glyph in the top row. Based on an SDF of a rectangle, a circle, and a plus-shaped union of two rectangles, we can just blend between these shapes based on a map attribute to get a nice glyph for representing signed scalars. We support standard time or arc length equidistant placement of glyphs, but since our arc length parameterization also allows us to check for overlap with neighboring glyphs, we also implemented a greedy strategy that places glyphs as densely as possible at original sample positions. This minimizes interpolation and is ideal, for example, for event type attributes. But of course, many other strategies are conceivable, including arbitrary user-defined placement, which we did not yet look into. Our U-coordinate runs along the tube axis and results from a reparametrization of the local curve parameter t running between subsequent position samples, which we call nodes n1 and n2 here. The orthogonal V-coordinate runs around the circular cross-section, silhouette to silhouette from -1 to 1, with the zero line exactly bisecting the viewer-facing cross-section arcs. V is very easily computed on the fly, as we will see in the next slide. U, however, depends on this global reparametrization function Sj, which, as we motivated before, gives us the arc length of the trajectory up to that point. And this needs to be pre-computed for every segment. For this, we do a 4-span polynomial approximation, which can later be evaluated very cheaply. And sigma j here is just the accumulated arc length up to segment j, which makes this reparametrization global. For the V-coordinate, the often used approach of using the angle to some reference direction would result in contraction towards the silhouette, as you can see to the right of this figure. But once we determine the direction from the tube axis towards the viewer, called E for I here, we can instead just directly project any point x on the surface onto an orthogonal direction, which also happens to be on the plane that would define a viewer-aligned ribbon. We can just use that to get a V-parametrization that behaves much more linearly towards the silhouette and will look very ribbon-like when viewed head-on. Obviously, we can trivially compute this on demand for any given surface point. Alright, and for implementing these concepts, we proposed a rendering pipeline which is fast, directly raycasts analytically described tubes, and perhaps most importantly, differs shading the tube surface until its visibility has been determined. We believe the latter is key to enabling our approach, as it limits the computational impact of potentially very complex on-tube visualizations, even for large and spatially complex datasets. We prototypically implemented it in OpenGL, but really any reasonably modern graphics API could be used. And for maximum scalability, the pipeline allows for switching the rasterization path to an NVIDIA Optics-powered image order raycaster on hardware that supports it. So let's now take a look at some results. I will first introduce the case studies we did, explaining one of them in some more detail, and then we will take a look at performance measurements. We came up with on-tube visualizations for 4 different datasets to validate the technique. Of these, 3 were sets of GPS trajectories with recordings of many internal state variables and events from sensors and controllers on board the cars and drones that moved. And these datasets were more of the sparse kind, which is why I want to present the large pathline dataset we looked at, shown here on the top, as to illustrate how important it is to also include ambient occlusion capability that, if we want to support all kinds of line data, has been shown repeatedly to help immensely with structural perception. The dataset in question came from the simulation of water flow through a fish-friendly weir, which also has a turbine driving a generator located in the large vortex structure in the center, which has a very clearly defined structure thanks to ambient occlusion. The simulation was done to assess whether fish would actually be able to migrate upwards through the structure, which would be prevented by high flow velocities or turbulence. Here we map velocity to tube color, allowing us to quickly make out problematic areas in red, which indicates 3 milliseconds or more from the overview perspective. The outflow region seemingly has enough non-red areas to suggest that velocities are overall low enough for fish to at least be physically able to swim through. However, upon closer inspection, we can see that even the slower, seemingly straight flows have extreme counterclockwise angular velocity, indicated by the very negative sine cliff at increasing pressure, as shown by the dark gray line plot. This indicates that flow there is still violently turbulent, just at a smaller scale, and this would have not been immediately visible with less attributes visualized. To wrap up the results, let's take a look at rendering performance. We did several experiments measuring the impact of our improvements to the rasterization technique compared to its previous incarnation, as well as comparing the rasterization path to hardware RT implemented in NVIDIA optics. First, on the hardware we used, all datasets rendered at very much interactive frame rates, no matter if viewed from far away or up close. For the latter, we believe the addition of visibility sorting to the rasterization path made the performance impact of changing viewpoints more predictable and more in line with the results we get from optics-accelerated raycasting. Note that this impact is caused by the ray intersection algorithm and not by on-tube visualizations. Their effect on rendering time is kept almost negligible by the deferred shading strategy. All right, before coming to a close, I also want to present some interesting questions for future work which came up while working on our case studies. One major problem, especially when dealing with object trajectories, is that they tend to stay stationary from time to time. Here, on-tube visualizations break down, and we want to investigate how this could be addressed. A potential solution would be to superimpose traditional time series plots for the affected period, which of course raises research questions of placement, occlusion, and the like. The other major point is perceptual overload. For this synthetic dataset here, we are visualizing 12 additional attributes, and this visualization is already pushing the limits of what a human can reasonably make sense of. Here we want to investigate if we can draw to channels other than color, like surface normals, as the reference grid can, by the way, already do, or properties of a physically based material. So to summarize, we developed a flexible pipeline for real-time trajectory visualization with many mapped attributes. We used the surface of tubes for that, which was enabled by a novel parametrization. The flexibility stems from using sign distance functions in conjunction with layers, and we achieve high render performance, enabling the technique to be used on very large datasets. Last but not least, I want to direct you to the OnTubeVis GitHub repository. The prototype exposes the full configuration space and provides plenty of sliders and knobs to play around with and create some nice OnTube visualizations. And with this, I'm coming to a close, and thank you very much for your attention.
Thank you very much for the presentation. And we have you online already. Hello.
Hello.
Hi. Are there questions? I start with a question. The thickness of the tubes seems to be a rather important parameter for the success of your technique. How do you choose it?
Well, I would say, very good question, by the way, that this probably depends a lot on the domain that the line data originates from. For example, if these are actual trajectories from an object, you would maybe want to select your radius to be somewhat equivalent to what the physical extent of that object would be. But of course, this can be tuned. If you need lots of data on the visualized on the tubes, you might want to choose a bigger radius, but we don't have any good guidelines here just yet. This is probably something that needs to be experimented on by the user then, or by the visualization expert that then uses the technique for some visualization for the domain experts.
All right, makes sense. Are there further questions in Slido? I don't see any. Then this closes the session. So let's thank all the speakers of all the 6 speakers again, and we close the session. Thank you very much.